Okay, for the rest of our review, we'll be doing a few short answer and then some multiple choice questions. Okay, the first question asks us, what is the smallest possible slope? That means we're trying to minimize y prime. In order to minimize y prime, we need the slope of y prime or y double prime to get our critical numbers. So if we were trying to minimize f, we would use f prime for critical numbers. If we're trying to minimize f prime, we use f double prime, etc. So on here, if I want to minimize y prime, the y prime values are not really the derivative that we need. We don't want the derivative y prime to equal 0. We're looking for the minimum value. So that really means that we want y double prime, which is 6x minus 6, to be what we set equal to 0. So that occurs at x equals 1. So now in order to test the number line, we have to do the y double prime number line where x equals 1. And if we test around that, we will see if y double prime is positive or negative. So if we substitute, for example, 0 into y double prime, we get a negative value. If we substitute 10 into y double prime, we would get a positive value. That means that the second derivative is negative and then positive, which means that we have a minimum on y prime, because y prime was decreasing and then increasing when the second derivative is negative and then positive. Now, it asks us what is the smallest possible slope. Right now, all we have is where that occurs. So we need y prime at 1, which is 3 minus 6 plus 5, or positive 2. So at x equal to 1, y prime equal to 2 is the smallest possible slope. Okay. Remember, you can pause the video at any time if you need more time or need to rewind and rehear something. Now, if a particle moves along a straight line according to the position function, s of t equals t to the fourth minus 4t cubed plus 6t squared minus 20, we want to find the maximum and minimum velocity. That is not the maximum or minimum position, but the maximum or minimum velocity. That means that we need the t value and the v of t value. We have to include the endpoints. This is the extreme value theorem. We have a closed interval. We have to have a table of values. And we need the critical numbers. Now, the velocity is technically the y value that we're going to try to minimize. So once again, we don't actually need velocity equal to 0. What we want is acceleration, the slope of velocity, to give us our critical numbers. So if we factor out a 12, then we actually only have one critical number at t equal to 1. So now, if we set the acceleration number line, we could figure out if that were maximum or minimum. But on the extreme value theorem, we only get the specific values in the table. So when we're doing an absolute max or min, it has to be the table of values. So what I want is the velocity at time 0, which according to the velocity equation would be 0. The velocity at time 1, which would be 4 minus 12 plus 12, so 4. And the velocity at time 3, which is 27 times 4 minus 27 times 4 again. If I substitute in, I have 9 times 3 times 4 plus 12 times 3 is 36, so this will actually be 36. So the 0 and the 36. So at t equal to 0, v equal to 0 is the abs min, and at t equal to 3, v equal to 36 is the abs max. And it's the min v, and it's the maximum of v. Okay, if we were looking for the maximum or minimum of acceleration, then we need the acceleration table of values, 0 to 3 in critical numbers. That means our critical numbers actually come from A prime, which would be 24t minus 24. So basically if t equals 1. So if we substitute that in there again, and we do acceleration at time 0, we get negative 24. Acceleration at time 1, acceleration at time 0, I need to go back to the acceleration function here. So the acceleration at time 0 would be 12. Almost substituted into the wrong thing. The acceleration at time 1 is 12 minus 24 plus 12, or 0. And the acceleration at time 3 would be 108 minus 72 plus 12, so 48. So at t equal to 0, acceleration equal to negative 12 is the abs min. And at t equal to 3, acceleration equal to 48 is the abs max. Now, the next part asks us to find the difference between the max and min acceleration. So very similar to what we just finished, acceleration is going to give me the values of acceleration. But acceleration's derivative gives me the critical numbers to figure out where acceleration has a max or a min. So that means that t would have to equal 2. So on our number line, or on our table of values, we're going to put t. We have to do both of the endpoints and then one critical number. Now we have to substitute not into the number line, because that just tells us relative max or min, but into the original A, so that we figure out what's the biggest and the largest. So if I substitute 0 in, I get 18. If I substitute 2 in, I get 6 times 4, which is 24, minus 2 times 24, which is 48, plus 18, which is negative 6. If I substitute 3 in, I get 9 times 6, which is 54, minus 3 times 24, which is 72, plus 18. So 0. That means we have a minimum value of negative 6 and a maximum of 18. So remember, you're not doing the time as your max or min. You're looking for the value of the acceleration. So the minimum acceleration is negative 6 and the maximum is 18. So the difference between those two is 24. Okay, now, the next part says I need to use my calculator to find the rate at which the gasoline in the tank of a hybrid car is changing. And it says at what time during the trip was the gasoline in the tank going down most rapidly. Going down most rapidly means we want to have the most, whoops, sorry about that, delay there, opening the calculator. It means I want to have the most negative slope, or in this case, the most negative f of t. Because it says the rate is modeled by f. So this is the rate. So we want to know when f of t is most negative. So now, what that means is that I would have to consider f prime of t, and we're actually looking for the absolute minimum, so most negative value. So f prime is actually going to tell me when f is a max or min. So I have 1/2 t to the negative 1/2 plus 0.5, the derivative of sine is cosine of t. So we want to set this equal to 0. So in my calculator, I'm actually going to type in clear these out. I'm going to put 0 in as the second one, and notice that I have moved over to the left and made a darker line so that I can see the 0 a little better. And I'm going to type in the derivative, which is 0.5 x to the negative 0.5 plus 0.5 cosine x. You could also put this in as a fraction. Just be careful if you have the old calculator that you actually put the fraction in correctly with parentheses. New calculator people, you can use the actual fraction feature. So now, on here, it says after a 6-hour trip starts. So really that means that t equals 0 to t equals 6. So that's really going to be my window for the x's. And then I'm going to zoom 0. Remember, zoom 0 only works if you put x values in first. So my window is 0 to 6, and then zoom 0. Now on my calculator, this is the graph of f prime. So that means I have a positive, a negative, and a positive y value of f prime, or that my f prime number line would be positive, negative, positive. So this is actually going to give me a max, and this is going to give me a min. So I'm going to consider this value in my table for f of t, and I also want to consider the endpoints. So I'm going to find, I could find both critical numbers, but if I know that this one is a max, I really don't have to find that one. So I'm going to use my calculator to find the intersection by second calc, number 5, and enter, and it'll find whichever one I'm closest to, so I'll move over to the right, or I could type in 5. If I type in 5, it'll move me over to the right-hand side of the screen, so I find the value that's on the right-hand side. Okay, so now the critical number that I need is 4.202, and I'm going to dot, dot, dot. I don't want to round off until I actually find values. So now back into my calculator, the nice thing is if I quit out of the graph, that x value that I was last on the graph is actually stored in there. So I can do the square root of x, and it knows the value of that x, plus 0.5 sine of x minus 2.5, and get negative 0.886. And that would be in gallons per hour, because F is actually a rate measured in gallons per hour. If I substitute 0 in, I could substitute on the calculator, but that's all going to come out to be 0, and then we would have negative 2.5 gallons per hour. And then if I substitute in the 6, I can actually copy this down, do second left arrow, and go back and change the x to a 6 in each of these parts. And get negative 0.190 gallons per hour. So that means that the absolute minimum value, or the most negative slope, actually occurs at time 0. So f of t is the smallest at time 0, meaning the rate is the most negative here. So the answer is A. Okay, now on this graph, the most commonly forgotten part is the initial value. The graph that we have is the graph of f prime. So f prime are the y values, which means f double prime would be the slopes. And f is actually the areas, but we have to remember the initial value. So on here, if I'm looking for the minimum value of f, that really means on a closed interval, I have to do a table of values, and I want to know the value of f. That should actually be an x. Sorry about that. And the critical numbers. The critical numbers occur where the derivative is 0. And that means the y values of this graph. So I can call those in here, I don't know, I'll call it number 1 and number 2 since they didn't give us specific values. We already have the endpoints 0 and 8. So I'll do it as number 1 and number 2. We're not looking for the x values. Remember, we're looking for the value of f. So at time 0, I already have 10. So if I go across to time 1, I lose 8. So I only have 2 remaining. If I continue across to time 2, I lose the other 2 that I had, and I'm left with 0. And if I continue across to time 8, I have 2 more. So I'm back up to 2. So the minimum value of f is 0. Okay, now, we use our calculator again and let f be the function defined whose derivative is f prime. Let a be a value of x where f attains its minimum value in the interval, and b be the value where it attains its maximum value in the interval, 0 to 2. Okay, so the minimum value and the maximum value. Let's graph f prime and see what's happening. So f prime is sine of x cubed minus 4x plus 2. I'm going to leave the 0 there. Window 0 to 2, zoom 0. So you notice the darker line is my y equals 0 that was in y2. So I'm going to calculate those intersections. We're going from 0 to 2, so my first intersection, if this is 0, 1, 2, would be somewhere around a half. So where it says first curve, I'll press enter. Second curve, press enter. And my guess is going to be around 0.5, so that we move over to find this intersection. Now to find the other intersection, I'm going to calculate, intersect, first curve, second curve. This one appears to be closer to 1.5. It doesn't have to be exact because it'll find the actual solution for you. Just make it move over. So now, since this graph has f prime as the y values, can't write the word value. Try that again. I have a positive, negative, and then positive. So I have a maximum and then a minimum. Okay, so that means that in here, the difference between these two values that are inside of that interval would be finding these two intersecting parts. So on here, we want to consider, if I have 0 initially, and my first critical number is 0.5392, and my next critical number 1.75, and then the last one will be endpoint at 2. If I initially have none for my f, because they don't give us initial condition, then this next part is going to be the only maximum within the interval. And we have to consider, though, this maximum, which is a local max, versus the 2 at the end. If I look all the way across at the area, I have none to start, then I have a positive value here. I lose more going across, and then I will gain some. But overall, the most positive addition up is just if we stop at the first max. So that's definitely going to be the max that we have. If we continue across, we have a negative value. So that's definitely going to be my min, because it's negative and it's definitely smaller than 0. And if I add after that time, I'm going to have more of a value. So this is neither a max nor a min, really. Because endpoints are either absolute or nothing. So the difference between these two on my calculator, remember the last value that I touch is actually what's stored into my x. So I could actually do x minus 0.5392. And the difference is 1.135 or 1.136. Okay. This next question is asking a similar type of thing, but we now have a rate in and a rate out. The Tastykakes came off the line, meaning that we are adding the rate in, and our box removed as a rate out. They're measured in hundreds of cakes per hour, so that's going to be critical. T is measured in hours. There are 500 cakes waiting to be boxed at the start of our 5-hour shift. So how long does it take the number of cakes to change from a minimum to a maximum? So what we want to do is do our 0 and 5, our time, and then our number of Tastykakes. I'll call that T. So we need to set the rate in equal to the rate out for every rate in, rate out question. So I'm going to change my equation to the rate in. Okay, those of you who have the old calculator, be very careful with your fractions and parentheses. So that's my rate in. I'm also going to put in my rate out. So it's going to be a fraction. And so I have 20x. And those old calculator people would definitely have to put parentheses around the 1 plus t squared. So if you have the old calculator, make sure you do that. I'll delete that 0. All right, now window 0 to 5, zoom 0. Okay, so that's the rate in. And now we have the rate out. So we're going to calculate the intersection. So the first intersection that I found is here, 1.869. Now, initially there are 500 cakes waiting. To figure out how many I have at time 1.869, I had the 500 initial cakes plus, since these are being measured in hundreds of cakes per hour, that means that I actually have to multiply the integral by 100 because it's not cakes. If I were just anti-deriving cakes per hour, I would get cakes, but now I need to multiply by 100 because of the rate. So then I'm going to do the rate in minus the rate out, and I can do that as one integral because of the fact that addition and subtraction are normal in calculus. So since I have that stored basically in my x now, I'm going to quit. If I wanted, I could store these in like a and b, but it's still in there. So if it makes you feel a little better about not using x all the time, we can store that into a. And now I'm going to do 500 plus 100 times the integral from 0 to a, since that's where I stored it. And it's the rate in minus the rate out. So it's the y1 minus the y2 because that's how I stored my equations. I stored it rate in the first. And then that is dx. So 269.469. Okay, remember we don't round off unless they tell us to. Okay. Now, I'm going to find the next intersection. Enter, enter, and notice that that one was closer over here to say 1. So I'm going to guess 1. Actually, sorry. Let me try again. Second calc number 5. Let's say it's closer to 0. So enter, enter, guess is 0. So it'll go closer to 0. And we get 0.30922. So I would do the initial 500 plus 100 times the rate. Rate in minus rate out, integral. So on my calculator, I can just go up if I quit and change the previous integral. Actually, if I want, I can type the x again just as a reference. That was the value. I can store that if I want into b. And that would be a very good thing to do on a free response question where you're using the same functions and the same intersections repeatedly. You want to store them and write down where you store them. Okay, so then I can go up and change that integral. So I'm going to grab. And the difference is, instead of doing the integral to time A, I'm going to do the integral to time B. So I'm going to type over the A, alpha B. So 573.283. And in order to verify where I have maximums and minimums, I still actually need to do the integral to 5. So I need that endpoint value. So instead of B, I'm going to have time 5. So 1167.441. Okay, which was 500 plus 100 times the integral from 0 to 5, rate n minus rate out dt. Now notice the wording. They ask us to find how long it takes to go from a minimum to a maximum. So time 1.86911 is the min. The max is the last point. And although this is a relative max at the first time, we need to change from a min to a max, a min to a max. So we're looking for these two. So that was my time A. So I can actually do 5 minus A, since I know that's where it was stored, at 3.3130.8. So that would be this one. Okay, so for the next one, they're giving me this, and I actually gave you F, and I changed it on my paper because you can't do natural log. So you want to copy this down as your F prime. Okay, now, it says determine which statement below must be true. They're asking us about relative minimums and relative maximums, where K is a constant and they have a critical point at x is pi. So if that's a critical point, that means that 0 equals K sine pi plus 1 over pi. Okay, so on here, in order to compare the concavities and points of inflection, we need the second derivative. Actually, let me double check. I might have written that down wrong when I changed it for review. I may not have changed the entire function and I meant to. I did not. I meant to have the derivative. Sorry. So I actually changed that function. K cosine. Sorry about that. So that means for a critical point to be there, that 0 has to equal K cosine of pi plus 1 over pi. So 0 equals negative K plus 1 over pi. So K equals 1 over pi. Okay, so using the fact that we have a critical point for our function at 1 over pi, that K would have to be 1 over pi. We can now do our second derivative by holding the K. The derivative of cosine is negative sine x. The derivative of 1 over x is negative 1 over x squared. So then the question is now, what is happening at pi? Do we have a relative min? Do we have a relative max? Do we have neither? Do we have points of inflection or nothing? Okay, so we already know we have a critical point at x equals 0. So what we have so far is that f prime of pi equals 0. That could be because we have something going flat. It could be because we have something going up and down, or because we have something going down and then up. So we don't know which of these zero slopes we have. Now, the easiest way to do this, rather than testing values into the first derivative, is to look at our second derivative. the second derivative at pi is going to be 0, because the sine of pi is 0, minus 1 over pi squared, which is less than 0. That tells us that the graph is concave down, which tells us that we specifically have the situation where we have a relative maximum. Next, we're going to consider the differential equation where f is the solution to the differential equation. At what point does f have a relative min? This basically is saying that y equals f. F of x is the function, the derivative of f is dy here. And we want to have a relative minimum. We have to think about what that means. A relative minimum means that we have to have our derivative either 0 or undefined. Since this is a polynomial type equation, it really means that dy dx has to equal 0. And to have a relative minimum, the second derivative would have to be positive, so that we have a little minimum right here. Okay, so if we just test all of the values n, or consider the values in the first equation. If I take 0, 0 and substitute into dy dx, I'm going to get 3. That means I have a positive slope, not a relative minimum. If I substitute negative 1 in, I get 1 minus 4 plus 3. So that is giving me a 0 slope, but I don't really know if I have a 0 slope as a min or as a max yet. If I substitute 4 in, we are going to get 1, which is an increasing slope. So that's definitely not going to be a minimum. We have an increase, not a max or min. If I substitute 0 and 3/2 in, we do get a 0 slope, but again, we don't know if we have a maximum or a minimum. If I substitute 5 in, I also get a 0 slope, but we don't know if we have a maximum or a minimum. So we have to do the second derivative. Now, before we panic about how hard that's going to be, when we take this derivative implicitly, it does have a dy dx in there. So that makes this a little intimidating. But we have eliminated all the points except those where the derivative was 0. So we made that happen first. So that really means that part's gone. So what we need to consider now is at each of these points, would I have a positive or negative concavity? So we're just looking at the x part. So if we use negative 1 as our x, then we have a negative concavity, which means we have a maximum. We're looking for minimums, so that's not it. If we substitute 0 in for the x, then that means we actually have a flat graph, a 0 slope with no concavity. So that's not it. Well, hopefully the last one works. If we substitute 5 in, we have a positive concavity. So that means that we have the positive concavity with a 0 slope, so that would be a minimum. Okay, for the next part, a tube is in the shape of a right circular cylinder. The height is increasing at a rate of 1.5 inches per second, while the radius is decreasing. So this time it's more like a toothpaste tube that we're squeezing, so nothing is staying the same. At the time that the radius is 4 and the length is 14, how is the lateral surface area of the tube changing if I give you the lateral surface area is 2 pi r h? Okay, so that means that we have the height is increasing at a rate, gives me dh dt is a positive 1.5 inches per second. The radius, however, is decreasing, so we're kind of stretching the tube longer, but then making it smaller around. So dr dt is actually a negative 0.5 inches per second, when the radius is equal to 4 inches and the length is equal to 14 inches. How is the lateral surface area of the tube changing? So the change in lateral area over time is a product rule. So it's the derivative of the first, keeping the second, plus the first, times the derivative of the second. So we're asking, what is the change in lateral surface area? So that's the part that we don't know. If we have a 2 pi dr h plus 2 pi r dh. And I did minus fractions because I do those better than decimals. So here, 2.5 are going to cancel, but I have a negative 14 pi. Still a lateral area over time. And for the next part, if the 2 cancels, I have plus 12 pi. So I end up with an overall negative 2 pi. And since it's area would be squared. Time is still in seconds. So look at what this reads. At what time the radius minus, how is the lateral surface area of the tube changing? So it's a negative 2 pi, which means decreasing at 2 pi inches squared per second. Okay, the next part says we have a sphere with a radius r, has the volume and surface area. These would always be given to you. The lateral area of that tube would also have been given to you. At a certain instant, the rate of decreasing of the volume is twice the rate of decrease of the surface area. So basically, since they're both decreasing, the negatives would cancel. So I really just want the rate of the volume is twice the rate of the surface area. So dV dt is 2 times dA dt. So now looking at what we have, if volume is 4/3 pi r cubed, then change in volume over time is 4 pi r squared dr dt. If the area is 4 pi r squared, and the change in area over time is 8 pi r dr dt. I can now substitute each of these into the corresponding part of the previous relationship. So that means that 4 pi r squared dr dt equals 2 times 8 pi r dr dt. So the dr dt's cancel, the pi's cancel, and I end up with 4r squared equals 16r. Now technically we never, ever, ever divide by a variable. So we could say r squared equals 4r, and technically we're supposed to solve this equal to 0 and factor out. So our two possibilities are r equals 0 or r equals 4. We're only throwing out the 0 and of course any negative value because this is a radius. Radius can't be negative, so our only answer is 4. Now, a part that's a cube would not be given to you. They expect you to know how cubes work. Okay, so it says at the time the block is x feet on each side, its surface area is decreasing at a rate of 24 square feet per hour. So the change in area over time is negative 24 square feet per hour. Now, surface area is not going to be given to you for a cube. You should know that a cube is like a 6-sided die. And what I mean by that is one of the number cubes, you know, dice that you play board games with. Okay, so it has 6 sides. Each of the 6 sides is a square. So the area of a cube is 6 squares, which are x by x. The volume of a cube is length times width times height, but since it's x times x times x, it's x cubed. So what is the rate the volume of the block is decreasing at that time? So we want the change in volume. So dV dt is equal to 3x squared dx dt. Now a is 6x squared, so dA dt is 12x times dx dt. They gave us dA dt, so negative 24 equals 12x dx dt. So if I divide both sides by 12x, I get negative 2 over x is dx dt. I can now substitute this into the volume equation and get dV dt is 3x squared times negative 2 over x, which is negative 6. X squared over x, one of them is going to cancel, so it leaves with negative 6x. Because it's volume, it's feet cubed per hour. So notice it asks, it's decreasing at what rate? So it's decreasing at 6x cubic feet per hour. Okay. Now on this part, it's one of those important questions where you have to pay attention to the direction. Gregory is getting closer to the intersection. So my y value is actually decreasing. So it says Gregory is traveling from the north 40 miles per hour towards the intersection, means y is actually decreasing at 40 miles per hour. And Matthew is leaving the intersection, so if that's our x. Then our dx dt says Matthew is traveling away from the intersection, getting larger at 25 miles per hour. It asks how fast the distance between them is changing. Let's call that z. Okay, so now it tells us Gregory is 3 miles away. Matthew is 4 miles away. So we should know that the 3, 4, 5 triangle gives me that z is 5 miles. Now we never substitute in until after taking the derivative unless something is constantly fixed. All three distances are changing. So x squared plus y squared equals z squared. 2x dx dt plus 2y dy dt equals 2z dz dt. I can divide everything by 2 just to make everything a little nicer. So now the x is 4 and is increasing 25 miles per hour. The y is 3 but is decreasing 40 miles per hour. The x distance is the z distance is 5 and we don't know dz dt, that's the question. So now we have 100 minus 120 is 5 dz dt. So negative 20 equals 5 dz dt. So negative 4 equals dz dt, and it would still be in miles per hour. So if the rate is negative, that means that z is decreasing. So the distance is getting smaller, or they're getting closer at 4 miles per hour. The next one says we have a right triangle whose legs are A and B and whose hypotenuse is C. Doesn't really matter where you put the A and B. It does matter that C is the hypotenuse. If the lengths of leg A and B are changing, but at a certain instant the area is not changing, which statement has to be true? Well, the area of any triangle is 1/2 base times height. But in this case, it's 1/2, the base would be A and the height is B. So they're telling us the rate is 0. Okay, the area is not changing, means that dA dt is 0. So that means if I do the product rule, dA dt is 1/2 the derivative of A, hold the B, plus 1/2 A is held times the derivative of B. It is a product with two different variables. So if this is 0 for area change, has to equal 1/2 B dA dt plus 1/2 A dB dt. I can cancel out the halves. And then one of these has to be the negative of the other. So whichever one I move over, if I look at my options, the A part is always positive. So if I subtract the B part over, negative B dA dt has to equal positive A dB dt. So notice that we have to have A goes with dB because of the product rule, so that's definitely not right. Okay. We can't cancel A and B, so this is the only correct option, because A is multiplied by dB, and it's negative B multiplied by dA. Okay. This next question has a lighthouse that is 2 kilometers from a point. The lighthouse is not running around. It is fixed position. However, a light is rotating around, so we have a theta, so that the light beam travels so here's our light beam, and it's going to travel along the coast. Okay, so the distance at the base is changing, and of course the length of the light beam is also going to be changing. What it tells me is that it makes 1 revolution per minute. 1 revolution per minute is talking about the angle changing, revolving around the angle. If the angle makes 1 revolution per minute, 1 revolution is 2 pi radians per minute. How fast in kilometers per minute is the beam of light moving along the shoreline? Means we would like to know what dx dt equals. When the beam is 1 kilometer away, so when x equals 1 kilometer. So in that case, I have to use the given information, not other things that I find, as much as possible. So that means I have the opposite and the adjacent, not the hypotenuse. So tangent of theta equals x over 2. So the derivative of tangent is secant squared times the derivative of the inside, d theta dt, is 1/2 times the derivative of x, which is dx dt. So if I look at my triangle, in order to do cosine of theta, I need a hypotenuse. The hypotenuse is going to be the square root of 5 based off the Pythagorean theorem. So cosine of theta is adjacent over hypotenuse. Secant of theta is hypotenuse over adjacent. And secant squared theta is going to be 5/4. So we'll substitute in 5/4 d theta dt, which we're already told is 2 pi, equals 1/2, and then dx dt is the unknown. So if I multiply, I have 10/4 so far. If I multiply by 2, I just get 5 pi equals dx dt. And of course, that would be measured in kilometers per minute, not kilometers per hour, because we can't change the time that's already in the problem. Okay, so right now we had 10 over 4 or 5/2. We multiply by 2, we get 5 pi. Now this got chopped off a little bit. The graph of the twice differential equation is shown. This is f. We want to choose which of these is in the correct order. Okay, so that means that we need to look at f of -2, and this graph is f, so f of -2 is 0. The graph has a negative slope, so f prime of -2 is less than 0. The graph has a positive smiling concavity, so the second derivative of -2 is greater than 0. So putting those in order, looking at this, the smallest one has to come first. So negative is the smallest thing. 0 belongs in the middle. And the second derivative, which is positive, would be the largest. So D is correct. And now for this one, I changed this to do the derivative for you since you don't know the derivative of E yet. So copy down now the second derivative of F. Okay, now, one important thing to remember about E, which we'll actually review a lot in the next unit, is that e to the x has a horizontal asymptote, is never 0. E to the negative x is just 1 over e, is just a decay function, also never 0. So this function is actually never undefined. So the bottom can never equal 0, only the top can equal 0. So that means that if I set the second derivative equal to 0 to get critical numbers for concavity, if I factor this out, we have x minus 5, x plus 2. Our only critical numbers are at x equals 5 and x equals -2. So I can eliminate e right away. So if I put those on my number line for the second derivative and test values. Okay, if I check a value such as -10, if I plus -10, I always put them into the factored form, and that would be negative times negative, so that's positive. If I chose 0, I would have negative times positive, so negative. If I chose something like 10, I would have positive times positive, so positive. We're looking for concave down, which needs the negative interval, so the correct answer is C. Okay, it looks like that's the end of our review. Hopefully this helped. I'll try to make more videos for you of our other lessons.